this one. Okay, so the next topic is really the next chapter, maps and matrices. We'll go back and review what we did last time with range space and null space and rank and nullity in a moment, but I wanted to do sort of the new stuff because it's actually pretty straightforward. So what happens is this. Let's say there's different cases. Like if I want to say, if I'm given a map, say x, y to x, y, x plus y, that's f is going from R to C to R 3C, from 2 vectors to 3 vectors. And then I could choose a base, each one of these is a vector space, and I can choose either a custom basis or the standard basis. So this is the standard, this is going to be the standard basis with 2 vectors. This will be the standard basis with 3 vectors. I could do a custom one, let's see, mark these as custom bases. And these are, so I could have 4 possibilities. I could have custom, I could have standard, 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 custom, custom, standard, or custom, custom. And each one of them follows the same pattern, but the easiest one to see is this one here with from standard to standard. So if I'm given this map, what I want to look at is the action of f on the bases, sort of like we just did. So what we want to find is we want to say, well, what's the image of 1, 0? Well, that's going to be 1, 0, 1. And the image of 0, 1, the other basis vector, if we're choosing the standard bases here, then the image of this one is going to be 0, 1, 1. Okay, now there's going to be a map. There's going to be a matrix that represents this map, the action of this map by matrix multiplication. And that matrix is given just by taking the columns as the images of the basis elements. So our matrix is going to be 1, 0, 1, 0, 1, 1 in this case. Now let's verify. See, this is a 3 by 2 matrix, and you're going to multiply it by 2 vectors. So let's see what is the image by matrix multiplication of this matrix on the 2 vector here, and see if it gives this. Well, I'm going to have 1 times x plus 0 times x is x, 0 times x plus 1 times y is y, and x plus y is here. So matrix multiplication by this matrix reproduces this, the image here. And in fact, matrix multiplication, linearity and matrix multiplication in some sense were defined so that this occurred. So it's easy, for the standard basis then, it's easy to find the matrix that corresponds to a map. Okay, so here we're going to use like lowercase letters for the map and upper the same letter but uppercase for the matrix that represents that map. Now there's going to be a different matrix corresponding to each map for each different choice of basis. So there's like one map but many representations because I have to also choose the basis. So we can look at this map and find different bases, and that's what we're going to do. Okay, so is this this is sort of the definition for this one case. We have a standard. Okay, do you want to go, should we look at, do you have any questions about this so far, or should we go on to the next one? The next one, we've done this one here. now I'm going to do this one here. This is sort of case A. One we shouldn't use. This is case 1. This is case 2 that we're going to do, and then we're going to do case 3 and case 4. Okay, any questions? Are you guys okay? Okay, let's do case 2. This is going to be the case B and standard basis for 3. Well, what you do is, let's say we're given the basis 1, 1, 1, minus 1. So we want to find the representation of this same map, but in this other basis. Well, what we do is we follow the same idea as look at how does F act on the basis elements. Here's the first basis element. What does F send that to? Well, it sends it to x, y, x plus y. That's 1, 1, 2. And what does it send 1 minus 1 to? Well, that's going to be x, x, y, and x plus y. It's going to be 1, 1, and 0. Okay, well, then the map, so because we have this, we sort of need to sort of say, well, this is the matrix from epsilon 2 to epsilon 3. And then the map here, the matrix rather, that represents this map, when I'm using this basis, is going to be basis B, epsilon 3, but it's the same thing. I just take the columns, the images of the basis vectors are the columns of the matrix. So you just have to find the images, given the map, find the image of the basis vectors, and you've got the map for these two cases at least. Okay, so we could check that again. But the thing is, if I put a vector here, x, y, it has to be in basis B. So let's say that I want to know what is x, y in basis B. Well, that's equal to x times the first basis vector plus y times the second basis vector. So if I put like choose some values here, that's not the same as doing it in the standard basis. If I wanted to know what the image of, say, 1, 1 was, I first have to translate that. In basis B, this vector equals 1, 0 in basis B. So I'd have to look at the image of that. So if I wanted to know what the image of XY was, say, to compare it with the other one, I'd have to translate this to basis B, which is a little bit of a linear system, but it's asking what is the A that corresponds to 1, it's going to be, we've done this exercise before, actually, in preparation for this. So our matrix can act, so if we want to know what the image of this is, we first have to find this, then do the matrix multiplication. But let's first so if I just do matrix multiplication in basis B, then I can just, do the matrix multiplication, and I'm going to get x plus y, and then x plus y, and then 2x. Well, this is the same map up here as this one. However, this is in the standard basis and the standard basis. Now, down here, this is in the standard basis, but this is in the weird basis. So we'd have to go through to check that this really is the same thing. we'd want to start from this. We'd want to say, if I want to start from a vector here in the standard basis, I'd have to first find what these A and B are, then use this formula here, and hopefully that would give me the same result as this definition here, and it will. Okay, so and we could go through the algebra of that, but I think it's going to be better if we sort of continue the story, because you can see now that it's easy to, as long as the target one is epsilon is the standard basis, it's easy. It's just you take whatever basis vectors you're given, find the images, and you've got the columns of the matrix that you want. However, now let's do the third case, or the third case being up here, a standard basis to a custom target basis. Okay. So let's do, it's the standard basis for the domain, but then D, let's say that is 1, 0, 0, 1, 1, 0, and 1, 1, 1. So we're using a non-standard basis. So we want to know what F is what the matrix that represents F is when we're using these bases. So what you do is you say, well, F, you want to find the image of F of the basis vectors, and we have the formula up here, x, y, x plus y. To give us the same vectors here, but these are not the columns of the matrix. We have to, because these are in the standard E3, so we have to transform them to the D basis. And that means we have to find, say, A times 1, 0, 0, plus B times 1, 1, 0, plus C times 1, 1, 1. Now, the answer is going to be, we have to do that for both of these, but so let's start with this first one here, and then we'll continue with this one. Okay, so this is like a linear system. Actually, if you look at it, it's going to be a linear system in which the augmented matrix is going to be 1, 0, 0, 1, 1, 0, and 1, 1, 1, 1, 0, 1. Okay, well, that's in echelon form, and you can see we're solving for A, B, and C, and you can see that the last equation is C equals 1, then B plus C equals 0, and since C equals 1, B has to equal minus 1. And since B plus C is 0, the first equation, A plus B plus C equals 1, well, that's 0, so A equals 1. Okay, so this first vector equals ABC, 1, minus 1, 1, 1, minus 1, 1 in basis D. Well, that's going to be the first column of our matrix, and we have to do the same thing for the other basis vector. We have 0, 1, going to 0, 1, 1. And we have to solve the same system. And it's going to be the same system, except this will change. So we'll have 1, 1, 1, 0, 1, 1, 0, 0, 1, and 0. So that the constant has changed, because that's what is the image of the standard basis. So then again, we find that C equals 1, but now B plus C equals 1, so that B equals 1, because if C is 1, rather B is 0. Sorry about that. B equals 0. And if B plus C is 1, and A, and then the last equation, A plus B plus C equals 0, and that's 1, then A has to equal minus 1. So that's minus 1, 0, 1. So this one here equals minus 1, 0, 1 in basis D. Let's see, minus 1, 0, 1. So therefore, my matrix that represents F in epsilon 2D is going to equal 1 minus 1, 1, 1 minus 1, 1, and then minus 1, 0, 1, minus 1, 0, 1. Okay, so, and again, these vectors over here can be, if I want to check, this is going to be in the standard basis, but the result, because this is E2 to D, the result's going to be a vector in basis D. Okay? So this one is almost as simple as the previous ones, but you have to you take the image of the basis vectors here, and then you have to resolve them into sort of the other components, because what you get is the image. What the formula you have is from standard basis to standard basis. Okay, the fourth one is just as easy as 3. That's from B to D. So let's look at that last fourth case. This one is F of xy to x, y, x plus y. The linear map corresponds to that, but we're going to use B equals 1 minus 1, 1, 1, and 1 minus 1. And D, well, it's like last time, 1, 0, 0, 1, 1, 0, and 1, 1, 1. And so what I do is I look for the image of 1, 1. Well, that's going to be 1, 1, 2. Then I have to reduce that. I have to, this is in the standard basis, so I have to put this into A 1, 0 plus B 1, 1, 0 plus C 1, 1, 1. And that's going to correspond to solving the linear system. 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 2. Okay, so this has the solution C equals 2. And doing back substitution, B plus C equals 1. Since C is 2, B has to equal minus 1, because minus 1 plus 2 is 1. Then you have A plus B plus C equals 1. And since B plus C is 1, A equals 0. So 0 minus 1, 2. So this equals 0 minus 1, 2 in basis D. And that'll be the first column of our matrix that represents F when it's operating on vectors in R2C and basis B and producing vectors in basis D. And so then we have to go and do the image of the other basis vector, which is X, Y, and we have to then represent that in terms of A 1, 0, 0 plus B 1, 1, 0 plus C 1, 1, 1. And that is the augmented matrix 1 minus 1, 0, which leads to C equals 0, this last equation. And then B plus C has to equal minus 1. Since C is 0, B has to equal minus 1. And since A plus, the first equation is A plus B plus C equals 1, B plus C is minus 1. So A has to equal 2, because 2 plus minus 1 is 1. So our vector up here is going to be 2 minus 1, 0 in basis D. So our matrix F that operates on vectors in basis B, taken to vectors in basis D, is going to equal 0 minus 1, 2, 0 minus 1, 2, and then 2 minus 1, 0. Okay, and that's all the possibilities. So it's actually pretty straightforward, but you just have to, the only thing you have to do is worry when the target one is different than the standard basis, because then you have to sort of find the representation of the vector that you're given here in the standard basis in terms of D. Okay, that's the whole story about finding, so the game is, given a map, by one means or another, find the matrix that it is, find the matrix that represents that map